All right. So, I remember when I was a sophomore, I first got involved in research and a few older undergrads. And I kind of wanted to join in the middle of a project, a lot of work had already been done. And so one of my fellow students in the group talked about having to solve some systems of ODEs, and they were using Runge-Kutta methods. And he said it was such reference. Runge-Kutta methods, I guess, like some really freaky, cool thing. So it was such a mystery about it. And I never learned about Runge-Kutta. Well, I guess it was the following semester when I took class similar to our 461, 561. And it was a whole semester about numerical methods for ODEs. And learned about Runge-Kutta then. And now the mystery is off. So now I think Runge-Kutta methods is like, eh. So, okay, how many of you have seen them in another class? Okay, yeah, well, yeah, you took them with me, and Haley would have seen them before, and did you? Okay, so yeah, so the shine's already off the apple, pretty much. So, oh well. Okay. And we've heard of Runge before because of Runge's example from Polynomial Interpolation. The idea behind Runge-Kutta methods is what we want are higher order one-step methods. As we've seen, Euler's method, forward and backward, those are both first order. We saw the trapezoidal method. Now that is the implicit method, that is second order. So the idea is we achieve higher order by evaluating our time derivative f at multiple points, ty. So we use different pairs. And we do this in such a way to match more terms in a Taylor expansion. Because Euler's method used Taylor expansion. It just matched the first term, the y prime equals f of ty. And then the next term, the second derivative term, was the local truncation error. So now we just try to go further. Okay. So what I'm going to do is I'm going to derive a very simple Runge-Kutta method that's second order, just to give you an idea as to how the process works. And then talk about the best known fourth order Runge-Kutta method. So as an example, derive a second order Runge-Kutta method of this form: yn plus 1 is equal to yn plus hf of, now instead of just tn yn, like in Euler's method, I'm going to add something to it. Tn plus alpha and yn plus beta. So something of wow, these notes suck. No, I mean, they're correct, from what I can tell. I mean, my every class today, Cal 4, I blew it pretty bad. It's like, so it's that kind of day. Okay. The thing is, since my textbook's kind of based on this, I think, okay, I have to keep this in mind to do it better there at least. Okay, but at least these notes will that you'll get from the board will fill in the gaps. Okay, so so one method of this form where alpha and beta are to be determined. So if we just had alpha beta equals 0, we'd be back to Euler's method. Okay. All right. So the way we're going to do that is by matching Taylor expansions. Okay. And since we want second order, we match terms of Taylor expansions through order h squared. So the idea is, like here we see an order h factor, but then when we take a Taylor expansion, we're going to get terms of higher order in h to match against. And so the rationale is, if we make sure, and I'll show you in a minute what exactly we're matching up. So we make sure that all terms of up to order h squared agree, then whatever's left over that we don't match is order h cubed and above. Now, keep in mind how we define local truncation error. Local truncation error, I would have something like this, and then I divide by h. So if I make sure that my leftover stuff is of order h cubed or more, then I have, what that means is my local truncation error is order h squared. And that's what I'm looking for, second order accurate method. Okay. So what is this matching up game that I have to play in order to get my second order accuracy? Okay, so what we match is item 1, Taylor expansion of y of Tn plus 1. So this is like the exact solution around Tn. Okay. Now, that would give me y of Tn plus 1 equals y of Tn plus h y prime of Tn plus 1/2 h squared y double prime of Tn, and so forth. We don't need to go any further than that. Well, in fact, yeah, we need to match through up to this point. I don't need anything past order h squared. Now, I then need to fill in the fact that y prime of t is equal to f of t y of t. So if I fill that in here, but hf of tn y of tn, and then second derivative is going to be the derivative with respect to t of f of tn y of tn. Okay. Now, remember your calculus, your multivariable calculus. How do I get this? What do I have to do there? I can't just say f prime. That doesn't even make any sense here. Because f is a function of two variables.
Chain?
Yes.
Chain? What was
It is a chain rule.
So you're saying like f prime that times?
Well, we can't say f prime
Okay, can't say.
because it's a function of two variables.
Okay.
What would I say instead?
Do you?
Yeah, partial of f with respect to t. Yeah. Okay. So we have Tn plus hf of Tn y Tn plus 1/2 h squared. So what I have is partial of f with respect to t. And I'm not going to continue writing this evaluation because lazy. And partial f with respect to y. And then here I need dy dt. Actually, I'll make up for my laziness by indicating that all this is to be evaluated at Tn y of Tn. But what is dy dt? What can I replace that with? Y prime, which is f. Well, you didn't give a correct answer. So. All right. Okay. So, and that's as far as I can go with that. So that's one thing I need. The second thing I need is a Taylor expansion of basically my method of yn plus 1 that I wrote over there. So really, what I'm expanding is f of Tn yn, or sorry, not that, Tn plus alpha yn plus beta around Tn and yn. Okay. So this here is a multivariable Taylor expansion. So what I'm going to have is yn plus 1 is equal to yn plus h. And then I'm going to have f of Tn yn as my first term in the expansion of this. And then, because this is a function of two variables, like here I have my value of a function at the center, then the derivative at the center times the change in t. But here I'm going to have two such terms. So I have partial of f with respect to t evaluated at the center times the change in t, which is alpha, plus partial of f with respect to y times the change in y. So that's going to be beta. Okay. Now, let's see. And in fact, do I need to? Yeah, I'm not need to. If I did need to go on, which I don't, but just for fun, to see how it works, I would go 1/2, and then I'd have second partial of f with respect to t times the change in t squared plus 2 times the mixed partial with respect to y and t times change in t, change in y, plus second partial with respect to y times change in y squared, and so on. Okay. Okay, so that's how multivariable Taylor's theorem works, or at least in this two-dimensional case. It involves all the partial derivatives, all possible combinations, and you see we actually have a binomial coefficient thing going here. And depending on which variable you're differentiating in respect to, that's what change in that variable you include here. Here it's with respect to t twice, so we have a change in t squared, and so on. The whole theorem for a two-variable case is written up in the notes. This is just the only part that I need right here. Okay. So now I just need to match this against this. Okay, so against that. So what we can do is we can just start matching terms up. So you think of yn and y of tn as essentially being the same, because we're just trying to figure out what values of alpha and beta would cause these terms to match. So for instance, these terms already match. There's no need to examine those. Here we have h f of tn yn. Here h f of tn y of tn. So these terms already match also. So there's no need to look any further at those. So it really boils down to these terms right here matching up against these. So if you compare these terms, and keep in mind there's an h floating out here. So in fact, what I'm going to do is, to make it easier, I'm going to factor an h out. So I can deduct one factor of h out here. So that way everything is in the same form. H is pulled out here, h is also pulled out here. Now, if we go ahead and match these terms against these, to make them equal, what should alpha and beta be equal to?
How about that term which is the alpha multiplied by beta?
Oh, that term?
Yes.
We don't need that.
Theorem.
Okay, ignore this. All right, because that's not what we need to match up.
Okay.
I was just showing you how multivariable Taylor's theorem worked, but okay. So what's left here, what I haven't crossed out here against that.
Alpha is half.
H over 2, yep. Well, dy dt, which is f. But what else do I need?
1/2 h.
Yeah. So 1/2 hf of tn yn. Yeah. There you have it. So by setting alpha and beta equal to those things, it turns out, in that evaluation of f, we can now put those back into the framework for method I have over there, and now we have a method that we know is second order. So now I can, okay, any questions about the matching? Of course, typical Runge-Kutta methods are way more complicated than this. You'd have to, if you want higher order, you have to expand out to more terms in both expansions, and you probably would need, well, you definitely would need more evaluations of f than this, so you'd have more parameters. And there's actually a lot of flexibility in how you can match terms to get the order you want. But this example, although a simple one, is enough to illustrate the general mechanism. Okay, so what does the method look like? I'll write it two different ways. So what we have is yn plus 1 is equal to yn plus h f of tn plus h over 2, and then yn plus 1/2 hf of tn yn. This is actually called the midpoint method. Because it somewhat resembles, it resembles the midpoint rule from integration. just like the trapezoidal rule from last time resembled the, in both forms, the implicit and explicit, resembled a trapezoidal rule for integration. Because what we have here, you can think of this as t n plus a half, because we're taking half a step. And you can think of this as y n plus a half, which is an approximation to y of t n plus a half. In fact, this approximation of y at the midpoint of the interval in time, so we're taking a midpoint in both senses, y at t and y, this is the approximation of this value computed using what method? Like if I'm at yn and I want to get to y at half a step down the road, what method was just used here to get that approximation?
Is it resection?
No. Big time-stepping methods, other time-stepping methods. Bless you. Euler's method. Because what is Euler's method? You start at your starting point, you add on evaluation of f at that starting point times your spacing. But here we're only taking a half step rather than a full step, which I hope resolves the pain puzzle look in your face.
Yeah,
Okay.
it does.
Yeah, because normal Euler's method is hf, but we don't want to take a full step.
Okay.
This is the midpoint method. Yeah. Okay. So it's because it's based on this idea. If you look at so it comes from the fact that from your ODE, you write an integral form like I've done before. Y of tn plus 1 equals y of tn plus integral tn plus 1 of f of s y of s ds. And what you do is you approximate this integral using the midpoint rule, which would be h f of tn plus a half y of tn plus a half. And what we could do is we could leave this as, we call this yn plus a half, and we get some freaky implicit method. But we don't want an implicit method, we want an explicit one. So this is approximated by forward Euler. Okay. With the step length of h over 2. Okay. Any questions about the method at this point? Well, it seems weird to take a first order approximation to this, that's what Euler's method gives you, and we still get a second order accurate approximation overall. But it's because of the symmetry of the midpoint rule. Now, okay, so this is one of the simplest Runge-Kutta methods. Although technically, even Euler's method is a Runge-Kutta method, but we don't really call it that. Because it's Euler's method.
Oh, okay.
Also, Runge-Kutta methods are kind of associated with high order accuracy, and this is not. Okay. Now, another way of writing, this is a typical way of writing Runge-Kutta methods, especially higher order ones than this. We use stages. So by stages, I mean evaluations of f. So you make these new variables. K1 is equal to hf of tn yn. And then K2 is equal to let's see, hf of Tn plus h over 2. And then here I can write this as Yn plus 1/2 K1. So that way we're writing this in such a way where we perform, where it's easy to see how many actual evaluations of f we need. And then once we have these, then we can say Yn plus 1 is equal to Yn plus K2. Actually, I wrote the explicit trapezoidal method in a similar way last time. That also had 2 stages because we had to evaluate at Tn and Tn plus 1. All right. And that's it. So this is the midpoint method, second order aggregate. Now, just so you can see the contrast, the modified Euler method, also known as the explicit trapezoidal method, can be written a similar way. So K1 is HF of Tn Yn. K2 is HF of Tn plus H Yn plus, instead of 1/2 K1, we just use all of K1. But then, so this is so here we're using f at Tn, here at Tn plus 1 basically. So then Yn plus 1 is equal to Yn plus, instead of just using K2, I use 1/2 K1 plus K2. So here we have a method based on the midpoint rule. This one's like the trapezoidal rule. And both of these are second order. Okay. Now, the best known Runge-Kutta method, and sometimes people just call this the Runge-Kutta method, but there's so many of them. And a lot of them are like named after people. Like, okay, the ODE solvers in MATLAB, like ODE 2.3 and ODE 4.5, are specific kinds of Runge-Kutta methods. They're really pairs of Runge-Kutta methods used together so that you not only approximate the solution, you also get an error estimate to vary the time step. That's not something we're covering, but it is going into my textbook. Buy the textbook. I'm kidding. No. You all get autographed copies for putting up with this. Okay. So fourth order Runge-Kutta. So to achieve its fourth order, we need more stages. There's 4 stages needed. So first we have HF of Tn Yn. K2 is HF of Tn plus H over 2 Yn plus 1/2 K1. So that's actually the same 2 stages we use for the midpoint method, but then we compute 2 more. K3 is equal to HF of Tn plus H over 2 again, but now we have Yn plus 1/2 K2. And then finally, K4 is HF of Tn plus H. Now we seek an approximation at the end of the interval in time, and we have Yn plus K3. Okay. And then we put them all together. Yn plus 1 equals Yn plus 1/6 K1 plus 2K2 plus 2k3 plus k4. All right, so that's 4-fold Runge-Kutta. So these things are very easy to implement in MATLAB. Well, I have code for this on the site, like for Runge-Kutta in particular, for this method. Notice that the stages that evaluate at the midpoint in time get more weight, these two. So can anyone tell me what integration rule does this kind of look like? One that gives 4 times as much weight to the midpoint as to the endpoints. Simpsons, yes. It loosely resembles it, but you can kind of see it, again, because of how much of the weight it gives on the endpoint. And Simpson's rule, a composite Simpson's rule, is 4-fold accurate. Okay. All right. Now, I have, don't feel like discussing it here, but I have an example on page 131 where I just pick out a ODE and I solve it using well, I guess where I know what the exact solution is, because this is just e to the minus t squared on the interval 0 to 1. And what I do is I use h equals 0.1, and I solve it using for Euler and 4-fold Runge-Kutta, which I abbreviate is often abbreviated as RK4. So if I use this step size, and if I want the error at the final time t equals 1. So for Euler's method, and it's not horrible. The error is about 0.038, whereas the 4-fold Runge-Kutta, same time step, same everything, it's 0.0000044. So totally blew it away. But it's also doing more work. But think of it this way. Suppose you're comparing like these methods, forward Euler versus 4-fold Runge-Kutta. Now you could say that the work needed by 4-fold Runge-Kutta is about 4 times as much. But first of all, this is way more than 4 times as accurate. The difference is huge. Also, for Euler's method, you cut the time step h by a factor of 10, the error decreases by a factor of about 10. You do the same with Runge-Kutta, 4th order, the error decreases by a factor of 10,000. So, you can see that the extra work done per time step is well worth it for the accuracy of the gain. Although something to keep in mind though, so like one of my colleagues at Stanford, Margaret Garrison, she actually doesn't, she's kind of against high order methods. And the reason is the kind of problems, ODEs, PDEs that she typically solves, the solutions have a lot of discontinuities. And when you have very bad behavior, the derivatives of your solution, or maybe solutions don't even have derivatives, then all those error formulas that we talk about all semester long, for interpolation, integration, etc., don't necessarily apply. So it's for such problems, there might not be much point in using a high order method. But there are a lot of very important problems where you can have smooth solutions, like the diffusive problems, where it still is a good idea. So something to think about. That your error formulas, it's not just a matter of, there's this h to the 4th in there. What does that h to the 4th multiply? Okay. Any questions about Runge-Kutta methods? Okay. Now, actually, the same issue came up in my other class in Cal 4, because I developed the notes using one textbook and then end up later using another. And sometimes these books express things in different ways. So that's something that can be quite a hassle. And this is, so I almost feel like I should apologize in advance in a way because I'm about to get to a new section, multi-step methods. And the way I describe multi-step methods is very different than what the book does. Now, who's being the weird one? I say they are, because I followed the convention from whatever book I was using years ago, which I also found being used in other books. But I guess there's a lot of dissension on this. So, as I present what a general multi-step method looks like, I will need to borrow somebody's textbook. Oh. All right. One of these days, Haley, I'll use yours. So that you can see how notation one maps to the other. Okay.
Sorry.
Okay. So now the name one-step methods will finally make more sense. So one-step methods they use information only on the interval Tn to Tn plus 1 to compute the solution at time Tn plus 1. So it's like whatever happened before that is completely irrelevant. But multi-step uses info from Tn plus 1 minus s. And this is for what is called an S-step method. So I'm going to use a parameter s throughout to refer to the number of steps. So in fact, if I have a multi-step method where s equals 1, that is a one-step method again, and these two expressions become exactly the same. Okay, so of course we care about the cases where s is greater than 1. So here is my general form. All right, well, so I write two general forms. First, there's in the notes, I have the summation on both sides of the equation, where I'm linearly combining y values. And really what I mentioned in yn plus 1, of course. And that is set equal to another sum, well, h up front. And I have different coefficients, betas, applied to values of f. Now the notation I'm going to use, I have these y's and I have my f's. So I'm going to use fi as a shorthand for f of ti yi. Again, because laziness. Now, so one thing we can see right off the bat about one-step methods, or multi-step methods as opposed to one-step methods is, in one-step methods, we're evaluating f at all these freaky times, like tn plus h over 2, and yn plus k1. Multi-step methods don't allow any of that. We have these ty pairs, and that's what we plug into f, and that's it. But because we have several of them, we're still able to gain high-order accuracy. Okay. All right, so this is a general form that you see in notes, but now I need to write the one in the book so we can try to associate them. And as far as problems and stuff, I really don't care what you use. Okay. So in the book, I'll try to make it as similar as possible. And for instance, they use the index j, but I'll use I. So I equals 0 to s, alpha I, y, n plus I equal to h. All right, so they also use alphas and betas, but okay, this is really annoying. For a deep for independent variable, they don't use t, they use x. These are initial value problems working in time. Why the hell would they use x? Okay, well, I hope you're not watching this. Okay. Okay. N plus I. Okay. So oh, so what's kind of weird is, so here, the goal here is to compute yn plus 1 from other values of y and the various values of f. Here, the goal is to compute yn plus s. Because you always want to compute the value at the latest time. Okay, and so here we compute yn plus 1 from yn, from yn minus 1, n minus 2, all the way down to yn minus s plus 1. Here, we compute yn plus s from yn plus s minus 1, yn plus s minus 2, all the way down to yn. And I and many other textbook writers like this form because that way all methods are described the same way. We're trying to compute yn plus 1 from other stuff. So that way the presentation of one-step and multi-step methods is kind of unified, but these guys didn't care about that. Okay, so so as far as how to because now the other thing that makes it even worse is here alpha 0 is associated with yn plus 1. And that's what you're trying to compute. Here we have alpha 0 is associated with yn. Also, alpha s is associated with yn plus s. So entirely different alphas are associated with whatever value you're trying to compute. Okay. So I guess a way to look at this is if you take my alphas and betas and reverse them, then you can get their alphas and betas. So it's probably the easiest way to handle it. Okay, so sorry for mix up, but I wasn't about to turn my notes inside out. Literally. Okay. Let's see. Okay. Now, so some basic facts about general multi-step methods before getting into specific ones. God, I feel like I'm going to still be behind, or every day I fall a little further behind, but we'll see how it goes. Okay, now the one convention that we impose is alpha 0 is set equal to 1. So the coefficient of what you want, yn plus 1. Because if I take a multi-step method, I can scale it by anything, by both sides of the equation, and it's still the same method. So here we just normalize by doing that. Okay. If beta 0 is equal to 0, then the method is explicit because there is no fn plus 1, which would be f of tn plus 1, yn plus 1. Okay. So that way you don't have yn plus 1 occurring on both sides of the equation. And so if it's non-zero, we say it is implicit. Okay. Now, as a condition to be consistent, and I mean consistent in the same way as I was talking about last time with one-step methods, that the multi-step method is consistent with the underlying ODE. We absolutely must have the sum of all the alphas has to be 0. Okay, and also the sum of all of the, well, okay, if we are, oh yeah, I have to be careful about that. The sum of all the betas must be equal to, for most methods it's going to be 1, but what we really want here is m, where m is the, the largest index, so that alpha m is non-zero. So however many non-zero alphas you have, your betas must sum to that, because the idea is you are approximating yn plus 1, but you're using information over a certain interval in time. And so what ends up happening is like as an example, if you have only yn plus 1 and yn on the left side, then all of your betas have to sum to 1. But if you have like yn plus 1, yn, and yn minus 1, then all of your betas must sum to 2. So this is to make sure that the local truncation error really is going to 0 as h goes to 0. Okay. Now keep in mind, this is assuming this condition here, that alpha 0 is normalized so that it's equal to 1. Otherwise, I'd have to adjust that. Okay. Now, I will talk more later about how do you ensure that a multi-step method not only is consistent, but of a certain order of accuracy. There's a very systematic method for checking that, but I'll get to that later. This condition here, alpha equals 0, ensures that the very trivial ODE, y prime is equal to 0, exactly, because the solution in that case is supposed to be a constant. Okay. All right. Now, here's some types of multi-step methods. Okay. So the first kind is Adams methods. Adams methods have a convention that, of course, alpha 0 is equal to 1, alpha 1 is equal to minus 1, and all other alphas are 0. So we only have those two terms on the left side, so it's just yn plus 1 minus yn. The general idea is to get to betas come from the integral form of the ODE. And the idea is this integral is approximated using a very strange interpolatory quadrature rule, in that we actually use interpolation points that are outside the interval of integration. Because we're integrating from Tn to Tn plus 1, but we use values of f further back from that. So basically we're passing a polynomial through the solution values. So we take this integrand, f of s, y of s, and we interpolate at these times, t n plus 1 minus s, n plus 2 minus s, and so forth, all the way up to tn minus 1, tn, and then optionally tn plus 1. So the idea is we include this point if the method is meant to be implicit, because that would involve yn plus 1, and it'd be on both sides of the equation. If it's explicit, we only use values up to tn. So basically we're using the previous values of a solution plugged into f, and we get, so we're passing a polynomial through f at those times, and then we evaluate the integral of that polynomial exactly. So it's just a very strange interpolatory quadrature rule. Okay. The accuracy is for an s-step method is order h to the s if the method is explicit, and then if it's implicit, it is order of accuracy s plus 1, which makes perfect sense in light of what it's told you, because if it is implicit, we're including another interpolation point. So the more interpolation points you have, the higher your order of accuracy will be. Okay. Okay, so that's one very important category we won't spend the most time on. Adams methods. Okay, I can say a little bit more about them. Okay, actually, I have an example in mind, so I'll go ahead and do that coming up right up. All right. Now, whoops. Okay. Also, these methods have different names. So explicit methods are called Adams-Bashforth. And then implicit methods are called Adams-Moulton. Okay. Which is things like this that make me wonder, what are the actual relationships among these people? Like, did Adams-Bashforth team up and mix explicit methods, and then maybe Adams is thinking, hey, let's do implicit too, and Bashforth's like, no, I want nothing to do with it. And like, oh, or maybe only Moulton worked on Adams-Moulton's methods, and Adams had nothing to do with it, but he felt, well, these are Adams' methods, just a slight change, so he included him in the name.
But kicked off Bashforth?
Yeah, I have no idea. I'm just speculating. Oh, all right, thanks. Kind of weird to have a comprehensive exam, just graded comprehensive exam, just handed to me, but okay. All right. Now, okay, so what I'm going to do here, whoops, I'm on the wrong page. Okay. All right. So as an example, I'm going to derive a three-step Adams Bashforth method. So that method is, well, at least the form of it, y plus 1 equals yn. So to be consistent with how I present one-step method, I just move a yn to the other side, plus h. And I'm going to have beta 1 f of tn yn. Well, I'll just write this as fn. Plus beta 2 fn minus 1 plus beta 3 fn minus 2. So notice the way I do this is like the subscript of the beta and the subscript of the f always adds up to n plus 1. So now I have to find the betas. So because for Adams methods, the alphas are known. It's just the betas that we need. Okay. So what I do is, since this is a three-step method, so I interpolate f of s, y of s, this is my integrand, at these 3 points, tn, tn minus 1, tn minus 2. So it's a three-step method, so I interpolate at 3 points. And what I do is, so I approximate my integral that I have from the integral form. Oh, actually, as far as I goofed, in the notes I have this as equal, but it really should be approximately equal. So I have this polynomial P2 of S. I say P2 because I have 3 points, therefore the interpolant is second degree, it's quadratic. But I can represent this in Lagrange form. So I can have a sum. Well, I won't do it. So I have fn times Lagrange polynomial degree 2 plus fn minus 1 Lagrange polynomial number 1, also degree 2, and then I have fn minus 2 Lagrange polynomial index 2. Okay. Now the f's I can pull out; they're constants. Okay. But before I go any further, what I can do is I can make a change of variable, a substitution. Let u be equal to tn plus 1 minus s all over h. So then du is equal to minus 1 over h ds. And what that does is it maps the interval tn to tn plus 1 to what? What interval would this become? Yeah. And what that means is my interpolation points are mapped to the integers 1 to s. In the explicit case, like this one, it would be mapped from 0 to s if implicit. So now I can form Lagrange polynomials that are much simpler than what I would have had otherwise. So now this integral becomes, okay, so I'm going to have a, so ds is h, okay, so I've got a factor of h that gets pulled out, and then I have fn integral from 0 to 1 of, I didn't call this L tilde, because these are the Lagrange polynomials that map to these points. These are the Lagrange polynomials that map to 1, 2, and 3. So I have fn minus 1 integral and then whoops, that's 1, 2. Okay. All right. Now, so now I can go ahead and okay, I'll write out in full what these polynomials are. Okay. So now I have, so beta 1 is just going to be the integral from 0 to 1 of a Lagrange polynomial that's equal to 0 at 2 and 3, and it's equal to 1 at 1. So I have u minus 2, u minus 3, over 1 minus 2, 1 minus 3, du, and then beta 2 would be polynomial that's equal to 0 at 1 and 3, and it's equal to 1 at 2. And finally, I have, this one's equal to 1 at 3, and equal to 0 at 1 and 2. Okay, so questions about where these came from? Okay. So then just go ahead and evaluate these integrals, and what you get is 23 over 12 in this case, and then minus 4/3 in that case, and then 5/12 in this case. So if you were to, you could check that all of these sum to 1. Okay, so now the final method is yn plus 1 equals yn plus h 23 over 12 fn minus 4/3 fn minus 1 plus 5/12 fn minus 2. So, and since this is a 3-step method that's explicit, it is third order accurate. So 3-step methods go all the way back to time tn minus 2. Okay. All right. Okay. And an implicit method, similar idea, but you include 0 as an interpolation point. So a 3-step Adams-Moulton method would have one term more than this. I'd have some constant times fn plus 1. Okay. Now, for an Adams-Moulton method, though, because it's implicit, one drawback is you need some root finding method, like Newton's method or secant method. To solve for yn plus 1. So that could be kind of impractical. But here's an alternative called a predictor corrector method. So there's 4 steps involved. P, E, C, E. So predict, evaluate, correct, evaluate again. What you can do is you use an Adams-Bashforth method and that gives you yn plus 1, but I'm going to call it yn plus 1 tilde, because that's not your final value. Then what you do is you plug that into fn plus 1, which is f of tn plus 1, and then the value you just computed, you put in there. Now you have fn plus 1 for your implicit, your Adams-Moulton's method. So Moulton, not Moulton's. With this fn plus 1, and that gives you your corrected value of yn plus 1. So you don't have to do an iteration at all. Okay, you can if you want by repeating these steps, but you don't have to. And then you don't want this to use for your next time step. You need to update it. So you take the value that you just got and you plug it into f again, and that sets up the next time step. So this will serve as the fn the next time around. Okay. So that way, you get the benefit of the implicit method in terms of order of accuracy without having to incur the extra work of iterating. Okay. Now, I have an example in the notes where I pick out 2 specific multi-step methods, Adams-Bashforth and Adams-Moulton, and I put them in a predictor-corrector pair. And the so I use a couple 2-step methods, but you can pair any 2 methods together. You have to keep in mind, though, the order of accuracy of the overall scheme depends on the order of accuracy of both methods. So if you use a low order for one and a high order for the other, the low order one wins. So keep that in mind. Okay. Now, all right. So that piece of chalk. So there's an example of that on page 135. Okay. And there's also sample code for predictor corrector on the site. Now, there's significant pros and cons, one of each, for multi-step methods in general. Okay. Now, as far as a pro is concerned, this is about efficiency, and you can get whatever accuracy you need from one-step or multi-step methods. Because you think, okay, let's compare a multi-step method like this one that uses information from previous time steps as opposed to, say, 4-fold Runge-Kutta, for example, that performs these certain number of stages, these evaluations of f during each time step. So in terms of efficiency, what is the advantage of, if you have a multi-step method and a Runge-Kutta method of the same order, what is the advantage of a multi-step method in terms of efficiency?
Faster?
Faster, why?
The requirements.
Yes, but
Because of the number of steps that we need to calculate.
well, like, okay, for example, okay, here, what?
Sorry. So are you reusing like
Yes,
function evaluations?
it's for
or
reuse.
something? Yeah.
because here we think, oh, we have 3 evaluations of f, but only one of them is a new evaluation.
Right.
That one. These were done before. So, yeah. So there's only one new evaluation of f per time step. Okay. Now, what about the drawback that actually is related to evaluations of that also? Because if we look at this method as an example, let's suppose I'm just starting the iteration. I have my y naught, my initial value. So I could say y1 is equal to y naught plus h f naught. I could get that. Minus f sub minus 1.
0.
I don't have it. I can't use it yet. So the con of multi-step methods is, at the beginning, you must use a one-step method for starting values y1, y2, and so on, up to ys minus 1. So for instance, for a 3-step method, you need to compute y1 and y2 using some other way, like a Runge-Kutta method, for instance, and then your multi-step method kicks in. So there's a bit more expense up front. And the key, and very important, the starting method must have at least the same order of accuracy as the multi-step method you're planning to use. So for instance, for that multi-step method over there, it's 3-step. I must use at least a 3rd order accurate 1-step method. If you want to use more, that's fine. But because if you use a lower order accurate method like Euler's method, that 1st order error contaminates your solution for all time. You'll never get rid of it. But the thing is, when I first learned about this way long ago, I thought, well, okay, if you must use a 1-step method to start anyway, why not just keep using it? Because of the efficiency gain. So your first steps may be expensive, but then they get faster after that. Okay. Oh, wow. I am... Okay, I want to see how far behind I am, but at least... because today I was supposed to get as far as... Today's the 16th. Oh. Zeros with consistency, so I have 1, 2, 3... Okay, I'm 3 pages of notes behind. Okay, but I should still be able to finish like the week after Thanksgiving, so that last week of class, maybe we won't have class. We'll see. Okay. Alrighty. So until